Good morning, teachers. My name is Supapitch Pichaichuang. My student ID is 673-040-652/6. Today, I will explain about the Taylor series and the Maclaurin series. First, the name of the series. The Taylor series is introduced by Brooke Taylor. He is an English mathematician. Introduced it in the 1715s, and the Maclaurin series come from Colin Maclaurin, Scottish mathematicians. Introduced it in 1742. First, we will start with the Taylor series that come first. The Taylor series is for turning a scary functions into a friendly polynomials. The Taylor series is the polynomial that can be used to approximate the values of the various functions by calculating the derivative at the specific point. So as we learned before, this is the summations of the power series that summation n equal to 0 to the infinity of c sub n multiplied by x power n. And this is the expansions of the summation. C in here is the coefficients. So this is the Taylor series. It looks like the power series, but you can see here that x is minus by a, but why? It because the Taylor series is similar to the power series, but it includes the term x minus a instead of just x to expand the functions around any point at a instead just at zeros. So this allows the series to represent the functions better at point other than x equal to 0. So the expansions of the Taylor series is just look like the power series, but everywhere we have x before, we plug in the x minus a instead. And after that, we substitute x by a. So the red highlight in here is the x that have been substituted by a, and you know and a minus a is equal to zeros. So the 0 multiplied by any numbers will always be equal to 0. So the functions of this one will have only left with c0 because it didn't have a or x in the first term. And for the second derivative, we derivative or the expansions we use with the differential theorems as we learned before. We will left with this one, and we do the same thing that we plug in a in everywhere that have x before we plug in a. So as before, it will only left with the first one that didn't have x or a in. So the first derivative of the functions will equal to c1. And the second derivative, we do the same things. And we will have the second derivative is equal to 2c sub 2. And if you want to find c sub 2, we change the size of it. So c sub 2 is equal to the second derivative divided by 2. And we do the same things with the third derivative. We will have these expansions, and we plug in a, and we left with the 6c sub 3. And if we want c sub 3, we change side, and we get the third derivative divided by 6. And we know that 6 is equal to the 3 factorials. So it will look like this. And we do the same thing with the fourth derivative. We have 24C4. And if we want to find C4, we change size and we will left with the fourth derivative divided by 24. And we know that 24 is equal to 4 factorials. So we will left with all of this. And if we take a look and compare with each term, we know that the number of the derivative is the same numbers at the sub of c's, and it will be the same numbers at the factorial in the denominators. So we can conclude that c sub n is equal to the n derivative divided by n factorial. So this is what we get that we proved before. And this formula is the coefficients of the functions where the absolute x minus a is less than r. So the summation that we taught before, that similar to the power series, we have Cn in here. So we plug in Cn that we proved from the last slide in. So we will get the summation from n equal to 0 to the infinity of the n derivative divided by n factorial multiplied by x minus a power n. So the series is called the Taylor series for f centered at a. This is for all x that belonging in the interval from a minus r to the a plus r, excluding the endpoint. Now we will talk about the Maclaurin series. The Maclaurin series is the Taylor series with the expansions about point x equal to 0. So we will put a equal to 0. So the summation of the Taylor series, everywhere that have a before, we will plug in a equal to 0. So we will left with the summations of the n equal to 0 to the infinity of the n differentiative multiplied by zeros divided by n factorials and multiplied by x power n. So this is the expansions of the functions of the summations in here. It will look like the Taylor series, but everywhere we have a, we will plug it in with 0. So we will have these functions. And this is the formula of the Maclaurin series. Now I will have an example for all of the series before the example for e to the x. We know that the derivative of e to the x will always be equal to the e to the x as the theorem taught. And we know that the e to the 0 is always equal to 1. So all of the derivative of e to the x that we plug in 0 will always be equal to 1. So now this is the expansions of the e to the x that we use for the series that we want to find the e to the x. The first one, we have the one that didn't have the derivative. The second one, we have the first derivative divided by 1 factorials and multiplied by x minus a power 1. And we calculate it, and we have the next term. It looks like the one that I told before. And we use the Maclaurin series, so everywhere that have a, we will substitute it with 0, so it will be Maclaurin series. So this is what we get, and as I told you before that f of zeros of this one, we want to prove about the x to e to the x, and e to the x, how many derivative they got, they will always get the same as the e to the x. And if we use the Maclaurin series, it will be e to the e power 0, so it will always be 1. So the functions in here will always be 1, and after calculation this one will be 1. 1 divided by 1 will only left with 1, so it will be 1 multiplied by x, and it will x in here, and this will be 1, and this will also be 1, and the factorial at the denominator we calculate it by expand it. So after calculation we have this this is the expansions after calculation, that the functions is the 1 plus x plus 1 divided by 2 multiplied by x power 2 plus 1 divided by 6 multiplied by x power 3. The ratio test is the one that we learned from the past, that we use absolute of an plus 1 divided by an, or we can use the absolute of an divided by an plus 1 is also the ratio test, but I will use this one for proving to find the radians. And for the an plus 1 of the summation in here, everywhere that we have n, we will have to substitute it by n plus 1. So the first one will be the x power n plus 1 divided by n plus 1 factorials, and divided by the x power n divided by n factorial is the origins of the summations, and we change the denominator to the numerator and the numerator to the denominator for it to can be easy calculation by, so it can be multiplied, and we expand the x power n plus 1, it will have the x power n multiplied by x power 1, and we cancel all the same variable, so we will left with the answer that x divided by n plus 1 in the absolute, and we know from the summation that n is the infinity, so it will be x divided by infinity plus 1 is the 0, so 0 is less than 1. The series converges for all values of x. The radians of the convergence will be the infinity. It will be infinite. So this is the final answers of the example for e to the x that I show you. And this is the reference that I use for making the video presentations. Thank you so much for listening for my explanations about the Taylor series and Maclaurin series. Thank you.